Right guys, just a little bit more info now on those subatomic particles. So we know that atoms are made up of protons, neutrons and electrons. Protons and neutrons are inside the nucleus, and the nucleus is really small but has all the mass. And we've got electrons around the outside in shells. Just a little bit more info now about the particles themselves, the subatomic, the protons, neutrons, electrons. The number of protons, the positive subatomic particles in the nucleus are really important, okay? The number of protons in the nucleus gives the atom its identity. So, for example, my identity, my name's Mr. Kippen, right? I have a certain identity. My genetics, my genes, my environment have made me who I am, all right? And you cannot change that. No matter where you take me in the world, I will always be me, right? And I'm cool with that. I'm happy with that. I've got some flaws, but I'm working on it. Every single atom has an identity, like we saw on the periodic table. So this guy here. Some atoms in the world are hydrogen, some are helium, some are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc., etc. They've all got a name, just like you've got a name, right? The thing that makes them hydrogen or helium or lithium or beryllium or boron is the number of protons in their nucleus. So if you're an atom, you're walking along, you got one proton. That makes you, let's have a look, that makes you hydrogen. You got one, right? That's called your atomic number. Your atomic number is sort of like your name. It's your identity. If I, as a chemist, if I see an atom and it has an atomic number of 1, I know it's got one proton in its nucleus, I know it's hydrogen, and I know it's the smallest atom that we know of. And I also know that if one hydrogen atom gets together with another hydrogen atom and bonds, it makes hydrogen gas. And when it does that, I know that hydrogen gas is flammable, and if I fill a balloon with hydrogen gas and light it up, it'll explode. So you can sort of see how it's fun. If you start to learn a little bit about the elements, you can start to go, oh, that's pretty cool, and you can make some explosions, you can have an understanding of how the world works, but you've got to start here. If your element has 2 protons, it has an atomic number of 2, it's helium. 3 is lithium, 4 is beryllium, 5 is boron, 6 is carbon, etc., etc. So the number of protons in the nucleus is super important. That's probably the most important thing about the protons. It gives the atom, its identity. They also, let's go back. So it's called the atomic number, okay? And it's also, they roughly weigh 1 atomic mass unit. So in chemistry, these things are really small, so we don't use grams often to weigh the mass of a proton or a neutron. So we've invented a new unit of measurement. You know, grams was invented one day, back in the day, so we've invented these things called atomic mass units, AMUs. And protons weigh 1, roughly. Same as neutrons, which is kind of convenient and nice. So that's protons, all right? That's the most important part about protons. They're positively charged and they give the identity to the atom that they have. So it's really important. The neutron doesn't change the identity of the atom. So remember, the protons is all about, if it's got 1 proton, it's hydrogen. If it's got 2, it's helium, etc. The neutrons, the green ones, the neutral ones that are in the nucleus, don't change its identity, but does change the mass. So these green neutrons they weigh roughly 1 atomic mass unit as well, about the same as a proton. And you can, within an atom, they can actually change a little bit. So some hydrogen atoms will have 1. They normally hang around the same number of protons as protons, so roughly they'll be the same. But you can sometimes have a little bit more, a little bit less than protons. So, for example, carbon has 3 different versions. We have 3 different versions of carbon. We have carbon 12, 13 and 14. Carbon 12 has 6 protons. I'm going to flick it up on the slide. Carbon 12 has 6 protons. Carbon 13 has 6 protons. And carbon 14 has 6 protons. So they all have 6 protons. It's carbon. If it's carbon, it's got 6 protons no matter what. But different carbon atoms can have different numbers of neutrons. Okay? So carbon 12 has 6 protons and 6 neutrons. It gives it a mass number. The mass number is the sum of the protons and the neutrons added up. So 6 plus 6 is 12. So we call it carbon 12. Some carbon atoms have 6 protons, makes them carbon, but also has an extra neutron, has 7 neutrons. So it's called carbon 13. It has a mass number of 13. It's different. Carbon also can have 6 protons and 8 neutrons. That's carbon 14. The number of neutrons doesn't change the identity of the atom, and it doesn't really change its it changes its stability. Okay, so for example, carbon 14 is radioactive. It breaks down. We actually use carbon-14 because it breaks down to try and date things that have been dead for a long time. Right? So it's called carbon-14 dating. Or nitrogen dating. So we can do that. So neutrons are less important than protons in a lot of ways, for us anyway, but they do change the stability of the atom, and sometimes it can make them a bit more radioactive or decay quicker, break down. But yeah, so that's what neutrons do. But it doesn't change the identity of the atom. It is called the mass number when you take the number of protons and neutrons and add them together. That tells you roughly what the atom's going to weigh in terms of its mass. So carbon-12 roughly weighs 12 atomic mass units. 6 plus 6 is 12, etc. The last one, the electron. This guy's important, all right? So the protons are important, the neutrons are important, but the electrons and the protons, man, that's where it's at, right? For us anyway in year 10. The electrons, we've already said they're negatively charged. I've already talked about how they exist in shells, and that the first shell can hold 2, right? The second shell can hold 8, the third shell can hold 18, or 8 for us. It's a bit weird, but we're just going to stick with 8 or 18. And they essentially weigh nothing. And where they live, their shells, how many electrons are in those shells, which is called their electron configuration, where are the electrons living, is so important. All right, I'm not going to tell you why right now, but it's so important that we, as chemists, can actually draw electron configurations. Where do these electrons live? What shells do they go into? The other important thing to note here is that normally in a neutral atom, like I said before, if you want to know how many electrons you've got in an atom, you go and check the number of protons, okay, the atomic number. Because if it's neutral, if you've got 6 positive protons in the nucleus, you have to have 6 negative electrons to balance it out. So there's 0 charge overall. 6 positives plus 6 negatives gives 0. So if you want to know how many electrons you've got and it's a neutral atom, so it hasn't got a charge on it, and we'll talk about those later, you check the atomic number, the number of protons. So that's really important. So electrons are super important. Here's a picture, I hope you can see all this. Here's a picture of the first sort of 10 atoms in the periodic table. You've got hydrogen, helium, lithium, beryllium, boron, all the way up to neon. Okay, so hydrogen's here. He's our smallest atom, we've already talked about him. He's got 1 proton, so he's got 1 electron. 2 protons, 2 electrons. 3 protons for lithium, 3 electrons, and see the third electron has to go into the next shell because the first shell's been filled already. And you go across all the way to neon. 2 in the first shell and 8 in the outer shell. And that outer shell is now full. Okay? Underneath each of these diagrams, and you can see this better on your PowerPoint, they've actually written the electron configuration. So instead of drawing, chemists are lazy, right? We don't like to draw pictures if we don't have to draw pictures. If we want to tell another chemist what the electron configuration is of a particular atom, we actually can just write them like they've written them underneath each of these pictures. All right? And it's really easy. So for example, boron has the electron configuration of 2, 3. What do you reckon that tells us? The first number, 2 electrons in the first shell, 3 electrons in the second shell. 2, 3. That's the electron configuration for boron. Super easy, right? And we can do that for any of them. So you're going to have a worksheet you can practice a few of those on. I don't need to spend, I don't think, too much more time on a video doing that. But, yeah, there you go. Okay? The other thing that you're probably useful to know is that when we, chemists again, lazy, and atomic numbers and mass numbers and elements, symbols, and that sort of stuff is important. So whenever we want to talk about an element in chemistry, we typically, you'll see this sort of thing written. This is called the atomic symbol. This gives us the symbol, the name of the element, so helium. It has 2 numbers attached to the symbol. We've got the number at the top, which represents our mass number. That tells me how many protons and neutrons we have in the nucleus, so there's 4. And the bottom number tells me just about the number of protons. That's its identity, so it tells me I've got 2 protons. If I've got a mass number of 4, and I've got 2 protons, that must mean that I've got 2 neutrons inside that to make 2 plus 2 is 4. Really important to know that, not too tricky, and yeah, so that's hopefully useful. Alright, so we're going to come back now to the question that we had at the start, right? The question was, why does sodium explode when we throw it into water? We now have a little bit of a picture about what atoms look like in general. So now let's go back and look at sodium. And let's see if we can find something that's interesting about sodium's atomic structure that might lead it to be really super reactive, right? To explode in water, which makes no sense, right? Water puts fire out. Why would sodium explode in it? So what's sodium's atomic symbol? Well, if we go back to the periodic table, I'm actually going to scan back here for a second. Let's find sodium. You've got to be able to use this periodic table, right? If you want to be a chemist in year 11 and 12, you've got to be able to use this bad boy. This is super important. There's so much information inside this guy. And I'm going to jump over this side because sodium's on this side, but there's so much information in the shape and the colours and the groups and the things called periods. There's so much in it. So cool. So let's find sodium. He's here. All right, Na. So if you can't see this on the video, pull out a periodic table on your slideshow. There's sodium. On the periodic table, the atomic numbers are written above the symbols. So we've got sodium has an atomic number of 11. So 10 plus a toe, right? 11. So if it's got an atomic number of 11, that means it's got 11 protons. And if it's got 11 protons and it's a neutral atom, they're balanced, how many electrons is it going to have? 11, right? So 11 protons and 11 electrons come together and make a sodium atom. It's got some neutrons thrown in there as well. So where do those electrons go? Well, let's have a look. Here we are. So I'm going to stay this side. So here is our sodium atom drawn for you a little bit. We've got our electron shells, we've got our nucleus, we've got our protons, which are red, and we've got our grey neutrons, which are grey and neutral. You can count the number of red dots in there, there'll be 11. And so therefore we've got to have 11 electrons around the outside, right? And they've got to fill those shells from the inside out, 2 in the first shell, 8 in the next shell. If we need a third shell, we go to a third shell. So let's have a look. We've got 2 electrons in the first shell. Cool. And I'm going to actually write, you may not see this, but I'll try my best. Let's write the electron configuration for this guy as we go. So his electron configuration, EC, equals 2 electrons in the first shell, 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell, and we've got 1 more shell. There he is. We've got 1 electron in the third shell. 2, 8, 1. That is the electron configuration for sodium, right? There's its symbol. So it's got 11 protons. Mass number of this sodium atom is 23. So that means how many neutrons does he have? 23 total, protons and neutrons, 11 protons. So 23 take away 11. So 23, 13, 12, right? So he has 12 neutrons inside his nucleus, and you can count those up. That's his electron configuration, 2, 8, 1. All right, so that's good. It's a good little skill to have, be able to write electron configurations. Here is, and you'll see this much better on your screen, right? So have this slideshow in front of you. Here is here's a diagram for the first sort of 20. Actually more than that, 5, 10, 15, no, 20 elements in the periodic table. And you can have a look at those for yourself and you can draw the diagrams, and they've also got the electron configurations underneath. Really important skill to do. Okay? So I'm going to leave that, that's your thing to do, to practice. There's a couple of questions on the PowerPoints, you can do that for yourself. Alright, I'm going to pause it there and come back.